Welcome to my presentation. While we move through the world, retinal motion might be due to our own motion because objects move in our environment, or of course both. So in principle, we would always want to keep track of our own movement in the environment and determine how much of the retinal motion is due to our own motion. Any retinal motion that is left would then correspond to object motion in the environment. To estimate self-motion, we have a range of cues available to us, very prominently visual cues. As here in this video on the right, where you can see the world fly past your observer while they're moving through this forest here. But also the vestibular system that keeps track of accelerations that act upon our body can tell us about how we move or are moved through the environment. And then there is a whole range of other information, like somatosensory cues, haptics, information from afferent copies, auditory cues, and so on. This self-motion information, and why I'm mentioning this here will become clear in about 2 minutes. This self-motion information is generally noisier than information relating to object motion in the environment. So our idea with this project was to look at how, or more precisely, how successfully we estimate object motion while we move or are moved through our environment. So there are a ton of different combinations of motion profiles and self-motion cues we could study here, and surprisingly few have actually been studied. There is some work on motion in depth and some work on rotational motion, so we decided to look at lateral motion here in this project to fill in some of the gaps. In terms of self-motion cues, we decided to get started with visual motion alone, but we might look at a combination of cues in the future once we can finally go back to the lab. So our first hypothesis was that we should compensate inadequately for self-motion in object speed judgments when self-motion is presented only visually. So in this case, with only visual self-motion, we would expect participants to underestimate self-motion. If they underestimate self-motion, then they would attribute part of the retinal motion elicited by self-motion to object motion. And this should then lead to an underestimation of object speed when the observer and the object move in the same direction. And that would correspond to lower PSEs, or points of subjective equality, and with that a psychometric function that is shifted to the left. The other way around, it should lead to an overestimation of speed when observer and object move in opposite directions, which corresponds to higher PSEs or a shift of the psychometric function to the right. The second hypothesis was that exposing participants to visual self-motion should lead to a decrease in precision, as they have to take into account noisy self-motion cues when estimating object motion. In the psychometric function here on the right, that would show as a less steep slope. To test these hypotheses, we came up with a psychophysical two-interval forced choice task where we showed participants two intervals of motion, and they had to tell us which of the two intervals was faster. You can see this here in the stimulus here in the video. We always showed them one big target and one target cloud. And we used these two different types of motion because otherwise, since the motion was always up for the same duration, half a second, participants could have just used the traveled distance to make these judgments. It would still be interesting, but not what we aim to study here. So while the big target ball was on display, the participants experienced visual self-motion, either in the same direction as the ball, in the opposite direction, or they could be visually static and not move at all. The speed of the big target was constant at one out of two speeds, and the speed of the ball cloud was controlled by an adaptive PEST staircase procedure. Now, we're actually publishing this as a registered report. So in the review of stage 1, before data collection, a reviewer pointed out that the wall in the background could basically serve as a frame that induces motion in the ball. And yes, this is me using the spotlight to sing the praises of open science. Anyway, so this effect of induced motion would go in the opposite direction of what we predicted for visual self-motion. And with that, it could make compensation seem more complete than it actually was. So we added also two control conditions. One, where the wall in the back was untextured, so before, and which shouldn't induce any motion at all. And a condition where the wall in the back was moving instead of the observer in the same and opposite conditions. So yeah, you've seen this here in the video. So let's go over the results. We have first here the results for the main part of the experiment. And let's start with the accuracy data. For accuracy, which tells us about how complete the compensation for self-motion was, we have the test conditions, same direction and opposite directions on the x-axis, and the difference in PSEs between these conditions and the static condition for each participant separately. So numbers above 0 mean that the target ball was perceived as faster than when the observer was static, and numbers below 0 mean that the target ball was perceived as slower than when static. We would expect the numbers to be around the dashed lines when our participants didn't compensate for self-motion at all, and on the dotted line here at 0 if they compensated fully. As you can see, on average, which is represented as large circle here, we have practically a full compensation when observer and target ball moved in the same direction, and a good but incomplete compensation when they were moving in opposite directions at about 80%. We analyzed this data using generalized linear mixed modeling and computed 95% confidence intervals, which we're showing here numerically on the plot. As you can see, they for both conditions, they include 0. That is, performance here was not significantly different from the static condition. But they were significantly different from the point of no compensation for both conditions. Have to admit that they are a bit wider than we had planned for with our initial power analysis. But there was just much more variability between participants than we had anticipated. Now, as for precision, we have basically the same plot here, but for the standard deviations of the fitted psychrometric functions. So numbers above 0 mean that the standard deviations were higher in the test condition, so precision was lower, and the other way around. So here again, we have practically no difference with respect to baseline in the same direction condition, while precision might be a bit lower in the opposite direction condition, but again, this difference was not statistically significant with the confidence intervals just including 0. Moving on to the control conditions, let's start with the accuracy data again. So here we have the PSEs for the blank wall condition, where we expected very similar results to the main experimental condition. And yeah, that was pretty much what we found. Pretty good compensation in the same direction condition and still an acceptable compensation, pretty good compensation actually, in the opposite direction condition at about 65% on average. And here we have the PSEs for the moving wall condition, where we tested the effect of induced motion in our stimulus. Here we found again no significant influence, but the problem is that due to this higher than expected variability that I mentioned before, this could easily be due to lacking power. So I'm not comfortable concluding that there was no effect of induced motion. So what if there really was an effect of induced motion? How would that affect the results in the main experiment? When there is self-motion in the opposite direction of the target, the wall moves, well, on the retina, the retinal image of the wall, moves in the same direction as the target. So any bias we see here, where the wall moves in the same direction as the target, should transfer to over here when self-motion and target motion go in opposite directions, and the other way around. So biases from this control condition here, where the wall moves in the opposite direction of the target, would also be present in this condition here. So induced motion might actually shift the PSEs downwards in the opposite directions condition and upwards in the same directions condition. And with that, it might mask biases due to self-motion, at least to some extent. All right, to complete the set of results, let's look at precision in the control data. In our self-motion with a blank wall condition, we found again no significant difference in the same direction motion profile, but we did find a difference for the opposite directions motion profile, where the precision was indeed significantly lower than when participants were static. And for the moving wall, where we wouldn't predict any differences since no self-motion was simulated, we indeed didn't find any differences. So overall, to give you a summary of our findings, we found that in our experiment, participants compensated on average fully for self-motion when they moved in the same direction as the target, and depending on the environment, to a larger or a smaller extent when they moved visually in the opposite direction of the target. And a potential reason for that might be that in the same direction condition, the target ball was much more centered in front of the participant for a larger portion of the trajectory. So there was a smaller component of motion in depth to this movement. And especially in VR, it is known that depth, and with that also motion in depth, are often underestimated. So that might be a reason for this observation. And further, we found that precision wasn't affected significantly by visually simulated self-motion in the main experimental condition, but in the blank wall condition that provided fewer self-motion cues, we did find that precision was indeed lower. And that is to some extent in line with previous results where a precision cost of self-motion had been found in an environment that was pretty sparse, much more sparse even than our blank wall environment. And finally, we also found no significant difference or no significant influence of induced motion. So overall, as take-home message, we found that we're actually pretty good at this task and mostly compensate well for self-motion, even when the only cues we have about the self-motion are visual. It might be a bit harder when we move in the opposite direction of the target, but still. And it does look like compensating for self-motion might be connected to losses in precision, particularly when the environment provides fewer cues to self-motion. And with that, I want to thank the Canadian Space Agency for funding my time doing research. I want to thank the entire team at the Multisensory Integration Lab for their feedback and support with this project. And of course, I want to thank you for your attention.